Right, so here we go. Start the material for the last exam. Let's just pop into it here. It is thermodynamics. The first thing we're going to do is review a little bit that supposedly you all learned in 1411. And of course you recall it all, but here we go. Okay, the first concept is that of enthalpy. And in layman's terms, this is just heat. It's just heat, but a special type of heat. It's heat when the pressure is constant. Okay, so enthalpy. Enthalpy is just heat under constant pressure, and you'll see why that's important. But first, we have to go back to talk about this thing called internal energy. Okay, here's the scoop, because this thermal is kind of confusing. And to be honest, it's still kind of confusing to me because they break energy into so many different forms. You've got physical, you've got chemical, and then you've got kinetic, and you've got potential, and you have internal energy, and you have Gibbs energy, and you have heat energy, and you have T delta S or entropy type. So there's a lot of types, and what happened was energy manifests itself in a whole bunch of ways. And so there's a whole bunch of terms for all of these. But the grand total, when you sum them all up, the amount of energy, the total amount of energy that a glop of something has, molecular vibrations and movement through space and heat, everything. If you sum it up, that's the internal energy. So we can think of that as just kind of sort of the total energy, but I hate to use that term because that's what I use for Gibbs free energy. Okay, so this is the total energy. Gibbs free energy is actually the total energy at constant pressure. And we'll get into that in a minute. Well, let me go ahead and tell you now. So why is this constant pressure a big deal? Because mostly chemists do things on a bench top, and the pressure is constant. The atmosphere is the same no matter where you go. We don't really do things in a pressure cooker, where when you heat them up, the pressure gets higher. So kind of sort of constant P, if you want to think about it that way, is everything you do that's not in a pressure cooker. If you do something in a pressure cooker, you got to add a whole bunch more terms to this. Okay, so anyway, so that's kind of the background. So if you think you're getting confused over this, it's okay. There's a lot to be confused on. Internal energy, the total energy. Let's go back to the first law of thermodynamics, the big one, the granddaddy of them all, which is paraphrased at the most common layman's term as you can't create or destroy energy. Okay, that's true if you consider matter a form of energy, and actually it probably is. Matter is just another form of energy, but considering it something separate for the moment, what the first law says is if you can't create or destroy the sum total of matter and energy, in other words, then those two terms added together are constant. Right? If you don't add something or subtract something from something, its value is constant. And so that's kind of where we are. Okay, so I forget I have a highlighter here. Right. Okay, here's another corollary to the first law. The amount of heat or energy lost is equal to the heat or energy gained. And that is for the system of the surrounding. Okay, now the first law applies only for the universe. And this is where it gets, if you don't understand this, if you don't pick up that one bit of information, then this whole thing gets extremely confusing. So it's very important to know the first law only applies at the universe. You can shift energy around from one part of the universe to the other so that one part loses energy and the other part gains. And this is where it oftentimes gets confusing is, oh, I thought you said you couldn't lose energy. Well, you can't at the universe level, but you can from a specific area. But guess what? Since the universe, which is represented by this box, is constant, I can move energy from one of these boxes to another. So this box did lose and this box did gain. but the net is the same for the universe. And that's what this next diagram shows. Why this is important is some questions are going to relate to the universe, some questions are going to be asked about the system, and some are going to be the surroundings. If you don't clearly understand those are three totally different entities and two different versions of the first law of thermodynamics are in play, it's pretty tough. Okay, so before I move to that diagram, let's put the first law, cast it in yet another light. Let's put it in math speak instead of word speak or equation speak. Okay, delta U, that is, U is the representation for internal energy. So this means a change in internal energy. As I do something in a chemical reaction, say, where I'm going A to B, this is a change. There will be a delta U associated with that. Now, of course, we normally know what we normally deal with is heat, right? That's normally what form. We don't typically talk about delta U. We typically talk about heat. Why? Because the reactions that I've given you so far were all done under constant pressure. And so heat is a good proxy for internal energy. Right. Okay. So the change in U is equal to the heat energy plus the work energy. What's the work energy? Well, that's the second big form. So how thermodynamics works is we take this grand total, the total of energy, and the first thing thermodynamicists do is they break it down into two pieces: heat energy and work energy. And then from those, they're going to have different expressions for each of those. Okay, that's a pretty long overview, but it's really hard to just jump into the text and get this stuff on your own. Once you realize that, and you can find your way around and kind of know when you read the book which of these areas it's talking about, it becomes a whole lot easier and a whole lot less confusing. Okay, so for example, heat energy, well, we know what heat energy is, right? The thermometer goes up or down. You have a change, and you have a certain amount. Every time you change, you've got a certain amount of heat that's given off or it's taken up. But there's also work energy sometimes. So let's say you expand a balloon, right? Okay, so we do a balloon, we heat it up, and the gases move around quicker, and the volume expands. Well, guess what? You've got something more than heat there. You've done work energy. You've applied a force. You've moved this balloon over a distance. In other words, it had to do work to push the atmosphere back. So if you want to know the total amount of energy for blowing that balloon up, it's the total amount of heat energy. How much did the molecular vibrations change? That's how much the molecules change. And how much work did you do pushing the atmosphere back? Now, what we've considered so far is just heat energy, but there's more to it. There's work energy. Okay. So with that, let's talk about these two terms in terms of the universe and then the two things that make up the universe. So let's take a quick look, and I don't think I have a good diagram here. That's not there. Yes, there it is. So I'm going to have to clean this up. Okay. So let's do this. This is what you definitely need to know. So this is kind of a review here. This is kind of a cleaned up slide. Okay. Internal energy is Q plus W. By the way, the U is always capitalized, that I've seen it. Don't get confused. Q can be capital or lowercase, and W can be capital or lowercase. Either one of these is correct. We know that the same is not true for something like M. Molarity is capital M, but small m is mass. So I appreciate usually when you see a capital and a lowercase, it means something different. It does not for heat, and it does not for work. With that as a background here. Okay, if we're going to talk about the universe and there being a couple of different pieces that comprise the universe, called the system and surroundings, let's kind of review that. And I like to just use two blocks. This entire block is the universe. That's it. And it means our physical universe, everything out past Pluto and the galaxy and the Milky Way and the whole thing. The whole thing is our universe. So anytime we do something, we can think about the universe as being made of two pieces. What's called the system, that's where the action is occurring, and the surroundings, that's everything else. So an analogy that I think is pretty fair is think about the universe as being a hermetically sealed house, and the system as being a particular room. And let's look at energy as just being dirt for the second. So if you've got a certain amount of dirt in your house, if you sweep dirt from the system, from this room into that room, this room gets cleaner. There was a delta dirt. Yeah, okay. But what do you know if your house is hermetically sealed? If this room got cleaner, what must have happened? This room must have got dirtier. Yes? Okay, so that's what we mean by system and surroundings. The system can gain or lose energy. The surroundings can gain or lose energy, but guess what? The universe is constant. All right, now what I want to do is go back and show you the diagram where we're looking at this change across this barrier, because this is the key. This is where chemistry is going to live right here, all of this. And then we'll get into some of the problems here. Okay, I'm going to highlight that. That is where chemistry lives. We do things in a beaker or flask, or we change things here. You are here. And what happens is the heat is either lost or gained. It just goes somewhere else. Yes. So your refrigerator is doing all this work, and it's getting cooler in the freezer, but something got warmer. Yeah, put your hand out the back of the refrigerator, and there's warm air blowing out. Yeah, why? Because that's how things work. If you're making something colder, something else got warmer somewhere. It had to happen. Why? Because the first law is true. Okay. With that as a backdrop and understanding, let's kind of get into some of the nuts and bolts. Okay, so here's your first tripwire, and it is a tripwire. It's the sign of things, the sign. We have to declare, we have to declare whether energy is moving out of the system or into the system. That's really, really important. And for example, if you're cold and you're trying to get warm and you're here, it makes a big difference whether your body is losing heat or your body is gaining heat. It's just, if you're trying to do a reaction and you need heat to kick it off, yes, it's very important that you know which direction Q is going. So in terms of math speak, they work that with the sign. So this is by convention. You got to know this. So if heat is lost from the system, Q is W. Okay? I'm sorry. Q is negative. So that's what we do. So if I tell you, and you know this. If I tell you delta H, or the heat loss for a system, is negative, you know what? You already know that's exothermic. What does that mean? Heat's given off, right? And that's what everybody says, given off. But when I ask them, what do you mean given off? Oh, I don't know. It's given off. Well, what's it? Well, I don't know. Okay, well, let me now tell you what the it is. The it is the system. It is giving off what? From the system. Okay. Wow, that didn't write with the crap, did it? Okay, so here we go. So here's your thing that you've got to know in light of all of that. Most textbooks, unless they tell you otherwise, are written from the perspective of the system. If you do not know this, whoever didn't come to this lecture today and doesn't bother to look back at it and doesn't realize that, this is going to be incredibly confusing. Most textbooks are written from the perspective of the system. So when it says exothermic is defined as heat is given, not just given off. More appropriately, when you get out of intro chem into gen chem, it will say heat is transferred from the system to the surrounding. That's what given off means. So you got to get out of that term of heat's given off or taken up. If you say that, you better know in your mind's eye you're referring to the system. Why? Because not all questions are from the perspective of the system. Okay. Every now and then we talk about things from the perspective of, a little bit of lag time there, from the perspective of the surroundings. Yes? So the surroundings can, quote, give off heat. Yes, the surroundings can give off heat, but that's what? That's not an exothermic, that's actually an endothermic. Why? Because if the surroundings give off heat, that means the system must have gained heat, not given off, but it gained heat. Okay, so I hope that's clear. You've got to know the perspective. When you read a question, you need to be real clear. I would assume it's the system, but if it gives you data that deals with the surrounding, you have to know. So let's talk about this in more specific terms now. So let me drive this point home. Okay. So let's talk about heat transfer. I'm just talking about Q now. Okay, so we know, I want to give you a graphic here. So if heat goes from the system to the surroundings, all of a sudden I have a great lag here. Okay, if heat goes from the system to the surroundings, that is exothermic and Q is negative. Remember, word speak says exothermic or heat lost. Picture speak has an arrow going this way. Math speak says Q is equal to negative. You must know word speak and math speak and picture speak. Okay? I've taught that over and over, but it's really important for thermodynamics because all three of these are used all the time. And each of them has an analogous, and that's the best I can do for you right there. Exothermic. There's your math speak. Word speak is, that's bad. Word speak is exothermic. And picture speak is this. Okay, so what's endothermic? Q is plus. Right? That's by convention, nothing else. Just by convention. If you see delta H is minus, you know it's exothermic. You know heat left the system. Typically, what is this system? Normally, it's the beaker. Actually, your system in chemistry is the chemicals that are actually reacting. If I've got a reaction going and water is the solvent, a lot of times water will actually be considered part of the surroundings, and just the molecules bumping is the system. Sometimes the whole beaker might be considered the system. It depends on what you're measuring and what's given in the problem. Okay, so the same thing is true for work, and this is a diagram that's out of your book. And I kind of wrote in here, I tried to kind of sort of put it in normal speak. So here, let's talk about Q. In this case, they draw the system as a circle, and they draw the surroundings. That might be a better way to do it anyway. Okay. So, for the system, for exothermic, heat leaves. Q is minus. If heat comes in to the system, we say Q is plus. Right. Okay. How about work? By definition, if the system expands, if the system does work on the surrounding, W, which is the symbol for work, is equal to negative. So that's just how they define it. Okay, I have read, this is by convention, but not always. You're kidding me. No, I'm not kidding you. There are physics books and other books that will call work done on the surroundings as positive. Okay, I guess somebody got their car started. Okay. And work done on the system, and think about that as the atmosphere pushing in on a balloon and making it smaller. The system shrinks. I've written that there. That's work equal positive. There are some physics books that actually define these opposite. So I will just tell you, for our purposes, this is the definition we're going to use. If you're going to some external source and you're trying to work some problem that has a work term, make dang sure you dig into there and find out when W is negative, is that work done on the system or work done by the system? And when it shrinks, oftentimes it's worded that way. Work is done by the system or work is done on the system. Okay, I've never seen anything that heat wasn't negative and positive. Exothermic wasn't negative. So this is a hard and fast rule. This is kind of sort of usually. Okay, and so I've drawn this diagram right here. So if my box here expands, then work is minus. And if my box gets smaller, then work is positive. Again, those are convention. And finally, I have outlined it one more time here at the bottom. So I spent a lot of slides making that, and I'll spend a reasonable amount of time here because it's a real tripwire. Okay, with that, we're going to go a little quicker. Oh, no. Okay. Don't worry about that equation just yet. Don't freak. Okay, here we go. So let's remind you what a state function is. And that's important because almost all thermodynamics functions are state functions. And recognizing a state function, what that means to you is, oh my gosh, it's a state function. That means I can do certain things to get to my answer easier. See, you don't care about the definition of state function. What you care is recognizing a state function because that tells you what you can and can't do with respect to solving a problem. Okay, so, but for the definition, a state function is something that is independent of path. And the best analogy that I could probably give, and you probably know this, is like climbing a mountain. Okay, the height is a state function, right? It's only so high. If you go from the bottom of the mountain to the top, it doesn't matter if you fly up at 30,000 feet and then parachute down, or you go all around the outside edge, or you just climb right up the edge of the mountain. It doesn't matter. You're at the same height. It was independent of path. Okay, well, how about something that's not a state function? Well, that's something that it is a function of the path. So in this case, the path you take, the walking path, is not a state function. Why? Because it makes a big difference. If you walk all the way around the mountain a bunch of times, you are in fact taking a longer path than if you just climb straight up the side. So there are both state functions and path functions in thermodynamics, and that will influence how you work particular problems. Also important is this idea of whether something is intensive or extensive. Thermodynamic parameters are extensive, meaning that the answer you get from a problem is going to depend on the amount of material there. You double the amount of material, you're probably going to double the thermodynamic parameter value. Okay, that's why that's important. Now let's dig into just a little bit of nuts and bolts. You do not have to know this derivation. Well, why did you put it then? Well, because one, the derivation will help you understand some of the things you can and can't do. And another, it's in every textbook, so I hate to not do it. Okay, so real quickly, let's talk about that. Enthalpy. Okay, this is weird. This is the definition for enthalpy. This is tough. And say, well, how does somebody think that up? Enthalpy is equal to internal energy plus PV. Really? Why do you do that? Okay, here's why it was done. People were smart. They wanted this term, delta H equal Q. They wanted some enthalpy term that represented the heat under constant pressure. So look down at the bottom here. So let me give you the punchline first to the joke, and then we're going to go back to see how the joke was constructed. All right? So here we go. So this is real important. They needed, because a lot of things are done under constant pressure. And, oh, that didn't work out well at all. I didn't have my highlighter. Hang on. Okay, so what we needed was a term, heat under constant pressure. Because when you do a reaction in a beaker, you're under constant pressure. And so you want to understand about that heat, only that heat, no other type of heat. Just give me the heat that came from the molecules changing their speed. I don't want anything to do with the heat of the balloon expanding or anything else. Why do we care about the heat at constant pressure? Because in chemistry, that's what tells us, remember the three forms of energy that atoms and molecules take. They vibrate, they rotate, and they translate. All that shimmy, shimmy, cocoa puff thing. Yeah, all that vibration and motion. That is temperature. That is the energy in an atom. So we want to talk about the heat part of that. Okay, so we need a thermodynamic term. Okay, delta H. Well, how do we get there? Well, if you take the definition for internal energy, which we've already given on another page, right? U is equal to Q plus W. We needed to find this term enthalpy, which is H, such that when you work it through the equation, you'll get the answer you want. Yeah, and so what that means is, it's really pretty clever, actually. It's really pretty clever. They said if we define enthalpy like this, and we go through a derivation and plug that equation in to delta U equal Q plus W, if we plug this definition into that, see, there's the U right there. We're gonna rearrange this for U and plug it in that equation. We're gonna wind up with this as an answer. Okay, so that's what's so confusing. This is just a bizarre term. I'm not sure I know what that means until I look at the bottom line. Oh, that's what that means. What that really means to me is, if you're at constant pressure, that's going to reduce to Q. Okay, so here's how they did it right quick. I'm not going to ask you this derivation on the test, but for those of you who are kind of geeks, let's look at this. Delta H is equal to U plus P delta B. Arbitrary definition. Thou sayest enthalpy is equal to internal energy plus PV. Okay, so if we have a change, if we move something from one station to another, if we have a change, we can easily say, well, delta H is equal to delta Q plus delta PV. Okay, so you people who have taken your little calculus class, your physics class, and you're so proud of yourself, which you should be, if you passed. Okay, so if I take the delta, it looks like that. Okay, and what I mean from the physics class is they'll teach you this. Okay, so, oh boy, look how much lag I have. Sorry about this. I'm gonna have to write very slow. I probably have a 5-second lag here. Okay, so delta P, the mathematicians tell me, can be broken down into P delta V plus V delta P. Okay, fine, if you say so. Okay, so here we go. So now, we're going to assume constant pressure. See, I care about constant pressure. So what does constant pressure mean? Constant pressure means, well, the change in pressure is equal to 0. So what does that mean? Well, see, there's a change in pressure. That's going to 0, so guess what? That term now goes away. Ah, it's a good thing they defined it like that, because that made part of it go away. Okay, now what do we have? Now I want to take away from the work part. I don't want to do work. Delta V and W are opposite signs by definition. Okay, so let's look at this. So now let's look at P delta V work. So my work term, this is my heat term. My work term is defined as pressure, and I'm pushing the atmosphere back. Okay, so P delta V, if I'm pushing it back, we're negative W. So I'm just going to substitute that in, my negative W for that. There we go. So my negative W here is just going to go to right there. And what is U equal to? Okay, well, I'm just going to bring my U term straight down from this equation. So now I have a new equation. Delta H is equal to delta U. Oh, but what is U equal to? U is equal to QP plus W. Expansion work only. Okay, so what do we have? So what's my internal energy? It's the heat energy at constant pressure. Yes, because I've already said this is constant pressure, and a work term. That's what U is equal to. But guess what? These two terms now cancel out, and you finally get to, oh my gosh, at constant pressure, the heat term at constant pressure is just, I could just call that enthalpy. Okay, there we go. So, finally the disclaimer, I cannot give this to any 1411, anybody like that, any intro chem. I can only tell you now because you know that. And here's what you now know. We've been using delta H, and I just tell my intro students, you know what, that's called enthalpy, but don't worry your pretty heads about it. Just pretend the H stands for heat, and you'll be okay. Yep. Okay, well, that's not true. But it is true under the context that I gave, because guess what I only give in 1411 and intro chem? In every case, I give them problems that only occur under constant pressure. And if you're under constant pressure, then indeed delta H is always just equal to heat. So this is actually true at constant pressure, but it's not true universally. Got it? And so that's why when you get into Gen Chem, we have to now, oh boy, that's a bad lag. We have to now start calling delta H equal what? Enthalpy. Okay? Granted, and this is true, most of the problems that you're going to deal with, delta H is going to be equal to heat. Any heat. But be aware, enthalpy does imply, if somebody says enthalpy or you read enthalpy, and you already know that implies you're under constant pressure. Okay, so there we go. I think I beat that horse dead enough. Okay, most of what you're going to have is just problems. But again, I'm spending time on this because it's very hard to ferret through this without understanding those and getting lost in the weeds. Okay, so we've talked about that. Okay, let's see. Enthalpy as a reactant or product. Okay, now we're talking about enthalpy. So there's three conventions. I'm giving you the background so you can work the problem after problem after problem, right? Okay, so let's go through these. I kind of dug these out of the text as three things that you need to know before you get there. The book teaches you these three things, but this on, some page, and this a couple of pages later, and maybe something else on the next chapter. So let's go back. 1. Delta H is associated with a particular chemical change with specified coefficients. Ooh, really? Yeah. So here's what you want to remember in thermo for sure. You don't see this 2 and this 1 in front of the O2 and this 2 as 2 atoms. Don't do it, don't do it, don't do it. You need to think about these in terms of moles. You've got 2 moles of this and 1 mole of this and 2 moles of this. Why? Because a lot of times in thermo, you're going to get questions, you're going to get equations that look like this. It's a common fare to get questions that look like this. And it's kind of freaky when you start talking about half of an oxygen molecule or half of something or half of a water molecule. It just seems kind of weird and uncomfortable. Well, what's half of a water molecule? I don't know. There is no such a thing. Well, it says 1/2 some equations because it might talk about half of water. Well, it says 1/2. Well, I know. What it means is half a mole. Okay, so if you think about that as mole, that's going to help you out with these. Okay, let's get back to this. Here we go. Why do you want to know it's extensive product? Because it's equal to a function of the amount of material. So if you change the coefficient, that means you change the amount of material there. Okay, so let's look at this. If I have 1 mole of this and a half a mole of this going to 1 mole of that, if I double it to 2 moles of this and 1 mole of this and 2 moles of this, I've got twice as much material there. So if I have twice as much material there, I'm going to give off twice as much heat. See, that makes sense, right? Look, like a log on a fire. You got 1 log. You got one log on your fire. You put another log on there. Guess what? You're going to get a whole lot more heat off. That's why you keep putting logs on the fire, yeah? Because you want more heat. Okay, why is all that true? Because the combustion process is an extensive property, and it's a function of the amount of material that's there. An extensive property, right? Intensive property was not function of the amount. Extensive property is a function of the amount. Okay, and thermodynamic problems are extensive. Now it just hit me. I think I said intensive a minute ago. Okay. Okay. Because all of these are a function of the path it takes to get there. Okay, so that's the first thing. I hope that's clear. Okay, next thing. And you probably know this from the thermodynamics, but hey ho, because of the way you set thermodynamics, right? You had to pay attention whether something was a solid or a pure solid or a pure liquid, because you would just drop that from the thermodynamic term. But if it was a gas or if it was a solution, you had to put the term. So just from your equilibrium work, you know that these can be important, okay? They're also important for thermodynamics. So I just want to note that some equations are specific for the phase. Sometimes that's important, sometimes it's not. Okay, let's look at the third thing you need to look for. Right. Representing delta H as a product or reactant when read, and you already know this. I've taught you this. For example, let's just one more time. Let's talk a little bit of word speak and formula speak and picture speak. Okay, so delta H. If you see writing delta H is negative, or you see the word exothermic, then you want to write your heat as a product. So if you have a reaction A plus B, and somewhere over to the side, or somewhere written somewhere else in the problem, it says, oh, by the way, 800 kilojoules was given off. Or it says delta H is equal minus. Or it says it's exothermic. Yes, any one of those three, you know this is true. If this is true, you can now write this in line. You can write what? Because this is negative, you can write your heat term as a product. We know this from our Le Chatelier work. Likewise, anywhere in the problem, if it says delta H is positive, or Q is positive, or it uses the word it's endothermic, or it just writes it out to the side in a table, any one of those things, you know now what? That's positive, that's endothermic. And if this is positive or it's endothermic, you write the heat term as a reactant. There we go. So I call that writing it in line, because you're what? You're writing it part of the equation. You're writing it in the same line. Okay, so now you know what I'm talking about. Okay, so there are two types then of inline problems. And so now we're getting into what you really need to know, or do for the test rather than know, do. Okay. Two basic types of questions. Just like there were two basic types of equilibrium, right? There were ones where you calculated K, and there were ones where you calculated concentrations from K. Two basic types. Well, the same thing is true here. Sometimes delta H is for a reaction is given, and you count delta H for a particular quantity of material. And sometimes the quantity of material is given, and you calculate delta H for the whole reaction. Okay, and that'll become hopefully clearer in a couple of minutes when we work a problem. Okay,